Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next several weeks, I will be releasing sample free response questions from each of the 4 AP Physics exams so that students can familiarize themselves with what kinds of questions will be asked and how the AP Physics exams will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day, so this video series is primarily intended to help those students. AP Central says students can expect to see these kinds of questions on the AP Physics 1 exam. There will be one question on experimental design, one on qualitative to quantitative translation, one paragraph length response or paragraph argument, and then 2 short answer questions. And the question in this video is type number 2, qualitative to quantitative translation. At AP Physics 1 2015 free response question number 3, which dealt with conservation of mechanical energy with friction. A block is initially at a position x equals 0 and in contact with an uncompressed spring of negligible mass. The block is pushed back along a frictionless surface from position x equals 0 to x equals negative d, as shown below, compressing the spring by an amount delta x equals d. The block is then released. At x equals 0, the block enters a rough part of the track and eventually comes to rest at position x equals 3d. The coefficient of friction between the block and the rough track is mu. Part A. On the axes below, sketch and label graphs of the following 2 quantities as a function of the position of the block between x equals negative d and x equals 3d. You do not need to calculate values for the vertical axis, but the same vertical scale should be used for both quantities. Part 1 is plotting or sketching the kinetic energy K of the block, and part 2 is sketching the potential energy U of the block spring system. I think this question is easiest to answer by considering the potential energy first. So our elastic potential energy is equal to 1/2 kx squared, which tells us that between 0 and negative d, our plot is going to be quadratic. It's going to look like a parabola. And now, from 0 to 3d, when the spring is no longer compressed, then there's no more potential energy stored, and the potential energy remains at a value of 0 for the rest of this span. And now we can answer the kinetic energy portion. We're going to need to remember that, energy is conserved. So our total energy between 0, by the way, this is from negative d to 0, the energy will be equal to kinetic plus potential, and it's going to be a constant value because that's what it means for energy to be conserved. So we can figure out what the shape of the kinetic energy graph will look like by knowing what the potential energy graph looks like. So when potential energy is at 6 blocks, kinetic is going to be at 0. And then when our potential energy is at 1, 2, 3.5 blocks, kinetic is going to be at 1, 2.5 to make up that difference to get to 6. And then when our potential energy is at 1.5 blocks, our kinetic is going to be at 4.5 blocks, again to total 6. And then when potential is at half a block, then kinetic is going to be at 5.5. And we can see that we can expect our completed curve to look like this. And now we can think about what's going to happen between 0 and 3D. You don't have to show this part yet. In fact, this work is going to show up later. But let's talk about it now. So what's going to happen next is that, friction is going to slow the block from 0 to 3D. So friction is going to be changing the energy of the system. So that implies to me that there's going to be work done by the frictional force. And that work, we're going to give it a negative sign because it's in the opposite direction of the displacement of the block. And that's going to be equal to, so negative friction times the displacement will be equal to the change in kinetic energy. So what's this showing us? This right here is showing us, we can actually, we could flesh this out a little bit more if you needed to see it before I highlight that. Like, let's finish that just in case it's helpful. So change in kinetic energy is equal to K final minus K initial. So let's rearrange this. K final equals K initial minus the force of friction times delta X. Well, gosh, this looks an awful lot like something that might be Y equals B minus MX. Oh, so in case you didn't notice it, from negative friction times delta X equals delta K, we have a linear relationship here between the kinetic energy and the displacement. So we're going to expect from 0 to 3D for our graph to look like this. So now let's talk about scoring. And there we go. So we are going to get a point for sketching either energy curve This is a lot of writing, actually. I'm just realizing that. So sketching either energy curve with a reasonably correct shape between x equals negative d and x equals 0. With 0 and the maximum value in the correct location. We are going to get a point. Guess I'll put it down here. We're going to get a point for sketching two curves from x equals negative d to x equals 0 with shapes and values such that the total energy is constant. Oops. Let me fix that. And there is a note with that, even if the curves are incorrect. So they are giving you partial credit for showing with your curves that energy is conserved, even if you didn't have the details of the curves correct. We're going to get a point for sketching u equals 0 from x equals 0 to x equals 3d. And then our final point is going to come from sketching kinetic energy as a linear function. From its max value at x equals 0 to 0 at x equals 3d. The spring is now compressed twice as much to delta x equals 2d. A student is asked to predict whether the final position of the block will be twice as far at x equals 6d. The student reasons that since the spring will be compressed twice as much as before, the block will have more energy when it leaves the spring, so it will slide farther along the track before stopping at position x equals 6d. B, part 1, which aspects of the student's reasoning, if any, are correct? Explain how you arrived at your answer. The student is correct that the block will have more energy when it leaves the spring. Since US equals a half kx squared, with a greater compression of the spring, the potential energy stored in the spring that can be transferred to the block is also greater. And our scoring here was just for a single point for stating that the block will have more energy when it leaves the spring. B, part 2, which aspects of the student's reasoning, if any, are incorrect? Explain how you arrived at your answer. So the student is incorrect about the new final position of the block because the spring's energy does not scale linearly with its compression. Since the potential energy equals a half kx squared, doubling the compression of the spring increases its potential energy by a factor of 2 squared, which equals 4. So our point here is for recognizing that the student is incorrect that the new final position of the block, about the new final position of the block, because the spring's energy does not scale linearly with its compression. Part C, use quantitative reasoning, including equations as needed, to develop an expression for the new final position of the block. Express your answer in terms of D. So, where do we want to start? We're going to go side by side and do a comparison for the initial situation. So, its elastic potential energy will be 1/2 kd squared. And then let's compare that to the new situation where we have an elastic potential energy of 1/2 times k times 2d quantity squared, which gives us 4 times 1/2 k d squared. So we can say then, that should actually say U2, not US. That should say U2. Let me fix that. So we can say then that U2 is equal to 4 times U1. Okay, now we need to talk about what happens after the spring has transferred its energy to the block. So we mentioned earlier that work would be done by friction. So we'll talk about work in the first situation equals the frictional force times the displacement for the first scenario. And of course, our force of friction is going to be mu times the normal force, which is just mg because there are no other vertical forces. And that initial displacement for the first situation was 3d. So we will also need to note that the work done in our second situation is going to be the same frictional force, μmg, but now times a new displacement that we're ultimately going to solve for. So now we can equate the work done in the first situation to the potential energy stored in the spring in the first situation. It is also true that the work done in the second situation is equal to the potential energy stored in the second situation. Well, that was just 4 times the original potential energy. The original potential energy is equal to the original work. So that means that 4 times the work has been done by friction in the second scenario, as was done by friction in the first. So now we can go ahead and do some specific substitutions here. μmg times delta x2 in place of work 2. That'll be equal to 4 times the work from our first situation, which was μmg times 3d. So the μmg's cancel, and we get delta x2 equals 4 times 3d, which is equal to 12d. So again, all we did there was use conservation of energy expressions when work can also be, changing the object's kinetic energy after that kinetic energy came from the potential energy. So let's talk scoring. We're going to get a point for indicating, there we go. I lost my cursor. It happens at least once every video. A point for indicating the final energy in the spring. Which becomes the mechanical energy of the block as it reaches the track, is 4 times the original energy in the spring. We are going to get a point for indicating that, there it is. Yep, I lost again. Man, let's get rid of that. We're going to get a point for indicating that friction remains the same. Specific, indicating friction remains the same. And then we are going to get a point for, and really this is going to come mostly from this line here, but we're equating initial energy in the spring to an expression that the energy dissipated by friction is proportional to the distance the block slides down the rough track. So let me finish that. And so really for the work that I've shown, this point is kind of really going to come more from um, this one and this one together, because this is how these two together are how we are showing a relationship between the initial energy in the spring and the distance the block slides down the track. Part D. Explain how any correct aspects of the student's reasoning identified in Part B are expressed by your mathematical relationships in Part C. Explain how your relationships in Part C correct any incorrect aspects of the student's reasoning identified in Part B, and refer to the relationships you wrote in Part C, not just the final answer you obtained by manipulating those relationships. So the student's correct reasoning that the block has more energy in the second situation is expressed by the calculations comparing the initial energy in the spring, and you could cite your equations here. The student's correct reasoning that the block will slide farther is expressed by the equation that indicates friction has to do more work to stop the block over the greater distance in the second situation. And the student's incorrect reasoning that the energy scales linearly with the spring's compression is corrected by the expression for the initial energy of the spring. Those three statements right there are exactly what the points were for. So I can still show you this. We'll get a point for, I didn't mean for that to be red, but it's okay. So we get a point for basically this whole first sentence. And then we get a, pen tool. Then we're going to get a second point. Did not mean to grab red, but apparently I did that again. Second point is going to come from this statement here. The student's, correct reasoning that friction is going to have to do more work to stop the block in the second situation. And then last but not least, gosh, since I've already been writing in red, we'll just write in red for this last one. And then our third point is going to come in here. Let's do a green highlighter with this final statement. So, you can cite your equations as needed here, but that shows you the scoring for this final part. So I hope you have found this demonstration of an AP Physics 1 question helpful. If you have a video solution you'd like to request from my YouTube channel, you can send it to physicsproblemrequests@gmail.com, although I won't be doing any new videos until the AP Physics series is over. If you need some assistance, you can send your question and the work you've done on it so far to freephysicshelpline@gmail.com. There's a limit of 10 questions per academic year. To learn more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics 1 exam, and those materials include the release-free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scores for that year were looking for and how they decided to award points. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.